In this lesson, we're going to learn how to graph transformations of the sine function. And we all know that the regular sine function kind of looks like this. And I'll just sort of sketch it down here below. We know that it starts at 0, it goes up to a maximum, down to a minimum, and ends. And normally, the period is 360 degrees in length, and it normally has an amplitude of 1. So if you recall, the period of a function is the length of time, if the time is on the x-axis, or the number of degrees it takes for the function to complete one full cycle. Okay, so the standard sine function completes one full cycle in 360 degrees. The amplitude is the distance that the maximum is away from the axis of the equation. And the axis of the equation is the middle of the equation. So you can see that we have an amplitude here between the x-axis, or the axis of the equation in this case, and the maximum. And we also have an amplitude here. And amplitude is measured as an absolute value. And just like rulers don't have negative values on them, we don't measure amplitudes in negative values. If this was a sound wave, the amplitude would control the volume of the wave. And on your volume knob on your stereo, you certainly don't have negative volume numbers. Okay, so the normal sine function has an amplitude of 1. It has an axis of the curve at y equals 0. And we have a period of 360 degrees. Okay, well, let's take a quick look at the function that we're listed here. We've got y equals 3 sine 2 theta minus 120 plus 1. Well, the first thing that my eyes are drawn to is the fact that we've got a 2 theta minus 120 inside the brackets. And normally we just want to have theta all by itself associated with, and this minus 120 is some sort of phase shift, like a translation left or right. So in order to correct this, we're going to have to factor the inside of these brackets. So instead of this being y equals 3 sine 2 theta minus 120 plus 1, we're going to factor a 2 out, and that leaves us with theta minus 60 in the brackets. Okay, so we don't want 2 theta minus 120. What we want is 2 and then theta minus 60. And you see how the theta is now all by itself. Okay, that pulls out this 2, and this 2 is the k value. Okay, so the equation we're actually going to graph is going to be 3 sine 2 bracket theta minus 60, and then plus 1 on the end. Okay, so be careful with that. If you see just one set of brackets and you see something like 2 theta, you need to make sure that you factor out and get theta all by itself. All right, so be aware of that. So let's take a look and see what we've got. Well, first off, this value at the end, this plus 1, that indicates where the axis of the equation is. And as we said, normally the sine function is centered right on y equals 0. In this case, the axis has been moved up to positive 1. So what I will do is I'm just going to go ahead and put the axis in right there at positive 1. Okay, and that will be our axis. So on the y-axis here, I'll label this. We're going to have a scale of 1. All right, that's where the axis is. What else do we know about this curve? Well, if we take a look at the front of the curve, we can see that the 3 here, that gives us the amplitude. So this will be the maximum and minimum height of the waves, and it is the distance away from the axis. So in this case, if the axis is at 1, the maximum will be 1, 2, 3 away from that. So I'm just going to put a maximum at right there, which will be at 4. And I'll also put in the minimum. And the minimum will be 3 away from 1, which is 1, 2, 3. So it'll be down here at -2. Okay, so there is the channel that this curve will sort of do its wave in. All right. Okay, well, what else do we need to address in here? Well, we have a k value of 2. Factoring allowed us to isolate this k value of 2. And what does that mean? Well, this 2 means that it can complete 2 cycles in 360 degrees. 2 complete cycles. So the period for that to happen must be 360 divided by 2, or 180 degrees. So that means that this function will complete 1 full cycle in 180 degrees. Okay, that little bit of information is going to be useful because we're going to use that to kind of decide how wide our graph should be. Okay, if we had a period of 720 degrees, we'd have to make sure we could represent at least 720 degrees on our graph paper. Here, 180, I don't think we're going to have much of an issue at all. Okay, last thing we're going to look at is this value inside here, this 60. Now, this identifies the phase shift. Now, the phase shift, we have to be careful. We expect to see theta minus. So if we see a 60 associated with that, we know that we are moving 60 degrees to the right in the positive direction. All right, so now that we know the phase shift is 60 degrees to the right, and we know that the overall period is 180, let's put a scale on our x-axis that kind of makes those two things very easy to do. So first off, let's look at the period, 180. So I know that I have to fit at least 180 degrees in here. Now I've got lots of room with all these grid squares, so I don't think that's going to be an issue at all. The 60, however, when I move by 60 degrees, it would be nice if when I do that phase shift, if I could line points up right on the grid lines. So why don't we take these grid lines and make each grid line represent 15 degrees. And how will that help us? Well, if I do tick, tick, and then tick, 3 15s are 45 degrees. And 3 more will be 90. 3 more, 2, 3, well, that would be 135 degrees. And then 3 more, 1, 2, 3, would be 180 degrees. So there's my 180. I've used most of the graph paper, and I've got enough ticks so that even if I shifted by 15 degrees or 30 degrees, it's going to line up nice and easily. I'm just going to go on and put 3 more ticks in, and that would be another 45 on 180, which would be 225, and 1, 2, 3, and another 45 in there would be 270. And so that should be enough degree measures for me to fit this in. All right, so how do we graph this? Well, first I'm going to realize this. I have the red channel, which indicates the amplitude. I have this light blue, which is the axis, so that's where going to be my zeros are. And the rest of the stuff, the period and the green phase shift, I can take into account as the last steps. But here's what I'm going to do first. I'm going to put in a regular sine function with an amplitude of 3, an axis of +1, and a period of 180. So I'm going to use that as my reference. So I know the sine function starts at 0, right on the axis, so I'm going to start it right there on the axis. After 180 degrees, it should be back on that axis. So I'm going to go there and put the 180. There it is right there. I know the sine function also has a 0 in the middle, halfway through. So in the 90, there we go. Okay? Now, sine function goes up first, and halfway between 90 degrees is 45. So up on there, on the red, is its maximum, and down here will be its minimum. So this curve that I'm drawing right here is a sine function, a little odd there, but that's okay. And it has an amplitude of 3, axis of 1, k value of 2, but it doesn't have the phase shift in it yet. But that's what's so good about making a reference one first. All I need to do now is take each one of these 5 reference dots that I put in and move them 60 degrees to the right. And on my grid, 60 degrees is going to be 15, 30, 15, 30, 4 of these squares. So I take this first one and move it 1, 2, 3, 4 squares to the right. This one, 1, 2, 3, 4 squares to the right. This one, 1, 2, 3, 4. This minimum, 1, 2, 3, 4. And finally, this last one, 1, 2, 3, 4. Okay? Now, drawing this curve, it will go up there, down there. I'll try and be a little better here. There we go. And there. So this green curve is the final answer for the function. It has the correct amplitude. It has the correct axis. It has a period of 180 degrees. And it has been shifted to the right with a phase shift of 60 degrees. Now, some of these questions might ask you to show one complete cycle. Well, there's one complete cycle. Well, what if it asked you to show one complete cycle starting at 0 degrees? Well, all you would do is you would draw your reference curve here, and then you would just move backwards to get back to 0 degrees. So 0 is back here, so we can see that it went 1, 2, 3 squares, and it went to its next key point. So I would go 1, 2, 3 squares, and that means it would be down here at a minimum. And then 1, 2, 3 squares, it would be back up here at a 0. And I'm just going to draw a smooth curve from there down and then to there. And I could, continue on and draw it to there. But essentially what you would do is if you were drawing this in light pencil, you could just erase this part here. There's a cycle going up, and then one complete cycle would get it right back to where it was, which is right about there, and then you could erase this little bit here at the end. Or take a highlighter and just highlight from 0 all the way until you get to 180, which would be right there, and then you have one complete cycle, okay, because your period was 180. All right, so there is a complicated looking transformation of the basic sine function, but if you just look for those hints and clues and you follow the steps, you should find graphing these to be quite straightforward.